All right, so now for part 2 of section 3.6, where we're looking at zeros of polynomials. Where are we? What are we doing? So now here's another theorem called the fundamental theorem of algebra. And it states every polynomial p of x, where n is greater than 1, so we're dealing with a quadratic or higher, and it has complex coefficients. So remember, that means not just real coefficients, but it could have imaginary coefficients as well. Then this polynomial has at least one complex zero. And remember, complex numbers includes reals. So if it has a real zero, we're covered, but it will have at least one complex zero. That means it could have an imaginary number in it. This is the fundamental theorem of algebra and the factor theorem together show that a polynomial of degree n can now be factored completely into n. I want you to add the word complex linear factors as stated below. So complete factorization theorem states if p of x is a polynomial of degree higher than 1, so it's quadratic or higher, then there exists complex numbers, which also include the reals, a, c1, c2, and so forth. And a can't be 0, otherwise the whole polynomial is 0. Now, I know all of this sounds very wordy. So what I want you to do is really put a star down here, because this is really the nuts and bolts of it all. If the polynomial has real coefficients, and if you do find out that you have a complex number as a 0, they're calling that number z. Remember, like a plus bi. It's a complex number. And we find out that it's a 0. Then its conjugate, noted by z bar over here, is also a 0. In other words, complex or non-real zeros always come in conjugate pairs, z and z bar. Like if we have a plus bi, then we know a minus bi is also going to be 0. So if they tell you 1 0 is imaginary, then we know immediately its conjugate is also a 0. So for example, they want us to find the zeros of each polynomial and its complete linear factorization. Again, finding the zeros, we can look at the possible rational zeros. So we've got factors of 4, plus or minus 1, plus or minus 2, plus or minus 4. And then the factors of 1, it's just plus or minus 1. So our possible zeros, we're going to divide all those. 1 divided by 1 is 1. 2 divided by 1 is 2. And 4 divided by 1 is 4. So those are all of the possible real rational zeros. Doesn't cover our complex, just the reals. But if we can find one of those, then maybe we can simplify that polynomial to find our others. Well, looking at that polynomial x cubed minus 2x plus 4, if I plug in just positive numbers, I'm going to get a really large positive number. I need a negative in there somewhere. So I can try p of negative 1. And again, you can use your table on your calculator. But this guy actually gives us 5, so he's not a 0. Let's try negative 2. And this guy does give us 0. So we know that x equals negative 2 is one of our real zeros. One thing that we can do to simplify this, we can divide and find out another factor that might be smaller. So if we divide negative 2 using synthetic into our original functions with coefficients of 1, the x squared term is missing, so we have 0, negative 2 for the x term, and then 4. Bring the 1 down, multiply, combine like terms, multiply, combine like terms, multiply, and we do in fact get 0 as our remainder. And this gives us an x squared minus a 2x plus 2 as our other factor. So this trinomial times the x plus 2 binomial are two factors of that polynomial. But we want to see if we can go further. Let's see if we can factor this guy, x squared minus 2x plus 2. Well, he's not factorable. There's no factors of a positive 2 that would add up to a negative 2. So we can do our quadratic formula. Don't forget your quadratic formula is the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So when we plug in those values, the opposite of a negative 2 plus or minus the square root of negative 2 squared minus 4 times 1 times 2 all over 2 times 1. That gives us a positive 2 plus or minus the square root of what looks like a negative 4 over 2. And remember our complex numbers, that square root of 4 is going to simplify to 2i divided by 2. And if we simplify that, I'm going to squeeze this in, we get 1 plus or minus I. Both the 2's have to be divided by 2 or nobody does. So now we need to do our linear factorization. Well, we already have the x plus 2, okay? So x minus a negative 2 is x plus 2. Here we would have x minus the 1 plus I, and then x minus the 1 minus I. Because remember, the signs are always opposite. So when we distribute those negatives, we still have an x plus 2 with the first one. We get x minus 1 minus I and x minus 1 plus I. Those are our linear factorizations. We're going to do the same thing with q. We're going to see if we can find zeros, see if we can reduce it. So on this polynomial, we may notice that we can factor out a GCF. So q of x, they have a 3x in common all the way across. So that leaves us with an x to the 4th plus 8x squared plus 16. And that trinomial on the right is a perfect square trinomial in that we've got an x to the 4th. So that would break down into x squared and x squared. And if we broke down the 16 into 4 and 4, that would also add up to our 8. So we get x squared plus 4, x squared plus 4. But notice they're wanting zeros and they want a linear factorization. I have two quadratic factors, an x squared and an x squared. So if we're looking for our zeros, we can take this x squared plus 4, set it equal to 0, and solve it. We get x squared equals negative 4. So x equals the square root of negative 4, which is 2i. And remember, if you get an imaginary 0, it's going to come in conjugates. So our zeros are of the form 0. That one comes from this GCF there because it has an x in it. Every factor that has an x has to be set equal to 0. And then the binomials x squared minus 4 gives us a positive 2i and a negative 2i. So when we write our linear factors, we get 3x. This gives us an x plus 2i and an x minus 2i. But we have two of these guys, right? We have this one for him. So we do it again, x plus 2i and x minus 2i. Gives us him. And we can clean that up. 3x times x plus 2i quantity squared, because we've got two of them, and x minus 2i quantity squared. Think about the terminology that we're using. They said we wanted linear factorization. And I said this is not linear because we've got quadratics in that factor. So that is a quadratic factor. But down here, it's linear. Even though that square is now on the outside, It's still a linear factor. It just has a multiplicity of 2 or an exponent of 2. In other words, 2 of them show up. So either of these forms here would suffice. Now for our last example, we want to find a polynomial with the following characteristics. It needs to be of degree 4. It has zeros. They told us that I is a 0 with a multiplicity of 1 and -2 with a multiplicity of 2. Now, if we only had those 3 zeros, because remember the -2 is a multiplicity of 2, that would give us a degree of 3, not 4. So remember what we said about complex zeros, we have to have our conjugates. So we would have P of X equals some leading coefficient A, we don't know what that is, but we have a 0 of I, so we would have X minus I, as well as its opposite, X plus I, and then a 0 of -2, so that would give us X plus 2 with a multiplicity of 2. Now, since we're coming up with a polynomial, generally our end result does not have the I in it. So we can go ahead and multiply those two together. Notice they weren't asking us to find the linear factorizations, they just said find the polynomial. So if we multiply, we can do that out here to the side, X minus I times X plus I. We distribute, we get X squared plus xi minus xi minus I squared. So these two add up to 0. And we get x squared minus, remember, I squared is the same thing as -1. So this gives us an x squared plus 1. So we'll put that back here, x squared plus 1 times x plus 2 quantity squared. Now we can use the point that they gave us, input of 1, output of 54, to find our A value. So we plug in 54 equals A times 1 squared plus 1 times 1 plus 2 quantity squared. That gives us a 2 times 9, which is 18A. Divide both sides by 18, and we get an A value of 3. So if we put all of that together, our polynomial P of X would equal 3 times x squared plus 1 times x plus 2 quantity squared. Okay, I know there's a lot in chapter 3 and you guys are such troopers. You're doing amazing work. But if you have any questions on any of these theorems or anything that we did in here, please do not hesitate to contact me. Okay, that's what I'm here for. See you guys soon.